Hey, workshop students. Let me help you with some general information about one-dimensional motion, and then we'll get specifically on this question. But hopefully what you got out of the reading is something along this line, that x represents the position of an object. And then the rate at which it changes, v, which you probably learned before this calculus class, was how its position changed with time. But if you take the limit as the time goes to 0, shorter and shorter amounts of time, if you will, then you would have calculus involved, and so this would be the derivative of position with respect to time, okay? And then, of course, the same thinking about acceleration, which you probably learned before this physics class, that it's the change in velocity with time. But again, if you're looking at the instantaneous, you're talking about a limit as the time gets smaller and smaller. It goes to 0, and so that becomes calculus, and so that becomes dv dt, or you could even write it as the second derivative of position with respect to time. And so what all this is saying here is there is a nice mathematical connection between velocity, position, acceleration, and time, those four parameters. Okay, so those four parameters I like to write this way, that if you know position, you can get velocity, and you would do that by taking the derivative. Oops, I messed up my chart already. You would go, well, no, maybe that's good. No, I'm going to do that. You would take the derivative of position, and you would get velocity. And then likewise, you take the derivative of the velocity, or you might say the second derivative of position, you would get acceleration. Now, hopefully from your calculus, you learned that the inverse operation of a derivative is an integral. So if you integrate then acceleration with respect to time, you would then get the velocity. And if you integrated then the velocity with respect to time, you would then get position. And so this is the mathematical connection. And this actually is the whole idea of one-dimensional motion, where now these four parameters, and so position, velocity, acceleration, and time, are all connected. Now, I say four parameters. Of course, remember when you do an integral, there's an initial, so we would also have an initial velocity and an initial position. And so you might say that there is 6 factors in all of this. And so we'll talk about the equations here in a second, but that's the connection. So this is true all the time. And let me just kind of highlight it and say, ta-da, there's the answer to every homework problem involving one-dimensional motion. And then you just got to work through the details. And I know that overly simplifies it, but that's the summary of this whole chapter. Now, I started this video with the idea of constant acceleration because there are some problems that you have constant acceleration and some that you don't. And this particular question came to me from your homework about constant acceleration, and I thought I would then use that as a springboard. But I see that questions earlier on and later on this homework problem don't have constant acceleration. So no, this is true always. This is Of course, I think harder if you don't have constant acceleration. But we have constant acceleration for a lot of problems. So I thought I would take this as an opportunity then to look at some really, really important equations, and starting with the idea that what if A is a constant? And so let me emphasize again that this is how you go between velocity, position, acceleration. And so, let's say they give you position and they ask for acceleration, you would take a derivative twice. Or let's say they gave you velocity and they asked for position and acceleration. Well, you would take its derivative and get the acceleration, and you'd integrate once to get its position. And there's all kinds of combinations that could be asked, and you have those type of problems. But what happens a lot, especially at the beginning here, is we have scenarios that have constant acceleration. A free fall being one example of that, where if you just drop something, it has a constant downward acceleration of 9.8 meters per second squared. But there's many other cases. You could have a car that has a constant acceleration. I was going to say that's probably not normal. A normal car might step on the gas hard and then ease up, and different changes would happen along the way, and therefore you would have different accelerations along the way. But it is possible to have a constant acceleration for a car, a dragster. But just the free fall is probably the best example of constant acceleration. But watch this. Let's go back to our chart here. And if you look at this chart here, this chart is saying that, okay, so if I'm given this, could I get an equation for velocity? And the answer is yeah, just integrate it. All right, so let me do that. So I go to integrate this, and I would say then velocity then is the integral of acceleration with time. And I would say, well, since acceleration is a constant, I can pull it out in front. And then, of course, once I integrate just dt, I get t. And then, of course, don't forget a constant of integration. Which then, if you study this equation here, you'll see that if you put in time equals to 0, this velocity would equal a constant. So this constant must physically represent the velocity at time equals to 0. Sometimes called the initial velocity. Although that can be a little confusing because sometimes initial velocity is not when you start your clock. So initial velocity and velocity at time equals to 0 may not be the same thing, but it usually is. So let me not make a distinction between initial velocity and velocity when your clock is 0. But I like the V naught here because it does say when time is equal to 0. All right, but what it gives you is what is often referred to as Kinematics Equation number 1. Let me put a little box around it and say this is the connection between initial velocity, final velocity, acceleration, and time. Now, maybe up here at the top, I should list the variables in here. Remember, I said that the acceleration, velocity, and position, all connected with time, are really the parameters that are represented in here. And then when you integrate them, you are going to then talk about the initial velocity and, I haven't gotten there, but initial position. And so you might say there's a total of 6 equations, and I'll give you some ways to think about this, some helpful hints, but this is our variables. Well, I'd like to call them 6 variables, and this is our parameters, and so our 4 parameters connected with our 6 variables. Like I said, this is the first one, and it connects 4 of them together. And so if you're given 3, you can find the 4th one. Okay. Now, if we continue on with this logic, we could get an equation for position also. And so I've integrated once to get the velocity. Let me integrate it again to get position. All right, so let me integrate it again. So I'm going to integrate velocity. That should give us position. And let's see what I get. I will put in the equation, which is V naught plus AT and DT. Maybe I will spread it out into 2 pieces. And then I will use my calculus accordingly. So this would be V naught t, V naught being a constant. I can pull it in front of the integral and I get just the integral of dt like we did up here. Okay? Because V naught is some number. And again, don't confuse V naught with V. V is not a constant, but V naught is. And then also, remember, as we said back here, that the acceleration is a constant. So let me pull that out. And then I just got an integral of t dt with an a out in front, which would become a t squared over 2. And then, of course, don't forget that every time we do a indefinite integral, there would be a constant of integration. So let me put the word constant here. I guess technically I have two constants, one here and one here. But if you'll let me just say two constants added together is one constant, and so treat that as one constant. And then if you'll let me stop and kind of read the math like we did back here and say, what does this constant represent? You can see also that at a time of 0, these would go away and your position would be whatever this constant is. So a good name for this constant is initial position, or x naught. Now, again, it really means the position when time is equal to 0. Sometimes an initial and 0 time aren't the same, as I mentioned back here. Like we could drop a ball from a tall building, and as we drop it and it falls down the building, maybe when we drop it, we call that initial. And then when it passes a window, we start our stopwatch and then continue on all the way down. So that starting our stopwatch would be then what's going on at time equals to 0. And our equations would need to be using that. And there would be a little difference between initial and time equals to 0. But that's, like I said, probably not a major distinction, but it can arise at times. All right, let me rewrite this equation in what's often referred to as kinematics equation number 2. And let me show you something kind of interesting here. Notice I didn't leave the x naught on this side because we could think of this quantity together as how far it moved. And so it's kind of nice to come back up here, and instead of thinking of these as two variables, a lot of time think of it as one variable, how far it moved. See, and so if you do that, you really only have 5 equations for these 4 parameters. And so our 5 equations are this: the acceleration, the velocity, the distance it traveled, okay, the time, and the initial velocity. So again, thinking of it this way can be an advantage that you have 5 variables and 2 equations. Now let me pause right here, because this is a good place to say I would encourage you to memorize these 2 equations. Okay, you're going to see them a lot. You're going to use them a lot. In fact, you're going to use them so much that even if you think you're not going to memorize them, you end up memorizing them. Now, notice all I did was integrate. So I'll go back to here and say that this is really the most important part of the chapter. If you just know this, which comes from this idea, you can do everything in this chapter. But you see that if I start with constant acceleration and have to integrate it every time I have a constant acceleration, it gets a little tedious. So you don't have to memorize these 2. You can derive them. You see I just did derive them. But they're not that hard to memorize. You use them a lot. Let me encourage you to memorize them. Of course, more importantly than anything, let me encourage you to memorize this chart. But I would also encourage you to memorize these 2 equations, because these 2 equations, as you see, connect the parameters of acceleration, velocity, distance moved, and time. And they have 5 variables in them. And so what that really means is you are often given 3 in a problem and asked to do these 2 equations and asked to find the other 2. That's kind of the summary of it. Now, we could even take this one step further and actually then use a combination of these 2 and come up with an equation that eliminates one of these variables. And what often is done first is the elimination of time. So if you were to solve this equation 1 for time, which I guess would become v minus v naught over a, and you were to put this into equation number 2. Now, I did that in my video lecture, so let me not do it again here in this kind of helpful video. But if I did that, then the combination of these 2 equations would give me what I call equation number 3. And equation number 3 then would be one that would eliminate time from that. And it would come out to look like this. It would be velocity squared is equal to initial velocity, or velocity when time equals to 0, plus 2 times the acceleration times the distance traveled. And so I'll put a box around this one because you'll find that you use it a lot. Okay? And here's where I start to question if it's worth memorizing, but I still say yes to that one. You know, like I said, these 2 are worth memorizing. Yes, you could derive them by integrating them. And then yes, this third one can be derived by first solving the first one and the second one. So technically, if you know the first and the second one, you don't have to bother with the third one. But if you do that, your problem gets kind of long where you have to take 2 steps. You first have to take equation 1, solve for time, and then plug it into equation 2. Now, not that that's real hard, but also not that it's real hard to memorize this one. And you use it a lot. And so it's probably worth memorizing equation number 3. Now, you can see this game can continue, and each time it continues, I would have to say less and less it's worth memorizing, because if you end up with too many equations, you overwhelm yourself, and you can't remember which equation goes where and what the limitations are. So I'm a big fan of fundamentals. So I'll say it again. This is all you really need to know. This is your fundamentals for this chapter. This one-dimensional motion, this is all you need to know. But again, for constant acceleration, these show up a lot. So just probably memorize those 2. This one, I'm going to again say yes, but I'm going to hem and haw here a little bit and say maybe it's not that important. But it's used a lot, so I'd say maybe so. Now watch what happens here a step further. I could take this equation number 1 and solve it for acceleration. So if I did that, I would get v minus v naught over t. And then I can put that into equation number 2 right here. And of course, if I did that, I would eliminate the acceleration. And so when I do that, and again, I do that in the video, lecture video, I call this equation number 4. You get distance traveled equals the initial velocity plus the final velocity divided by 2 multiplied by time. Which I like to think of this, since you've got a beginning plus an end divided by 2, that's an average. That's average velocity times time. I'll put a box around this, and then I'll say, I don't know if this one's worth memorizing. Because again, like I said, we're getting too far along in the sense that all we're doing now is memorizing a bunch of equations, and that's really not going to serve you well. I hope you will learn right away that, taking a physics class and just memorizing a bunch of equations and spitting them back out doesn't work so well. I mean, it works okay, and you'll get an okay grade, but it's not really the way to go here. The idea is to know the the fundamentals of what's going on in the physical world, and that's it. And so none of these 4 equations are needed if you know this. Okay. However, like I said, 1 and 2 are used so often, they're worth memorizing. They're not that hard. So is 3. And then this one's pretty easy to memorize. That's why I say, I kind of hem and haw said, we're getting too many to memorize. But at the same time, this is easy. It's just distance times time. Well, it's average velocity times time. And average velocity is beginning and end, right? 2 numbers. You take a beginning number, you take an ending number, and you add them together, divide by 2. Okay? So that's what I mean by that. So we use it a lot, and it's a good one to know here. So I'm going to leave that up to you because, again, the same game can be played here. We could do this a 5th time. And at this point, I'm going to say, no, don't memorize this. This is just getting too much. But if I took equation number 1 and solved it for initial velocity, and so here's initial velocity, I would get velocity minus acceleration times time. And if I put that into equation number 2, okay, I would eliminate yet the next variable in all of this. And let's see, what would I get when I did? I don't do this one enough. It looks like I'd get distance traveled plus 1/2 AT squared is V over T. And so I guess I could call that kinematics equation number 5. And I'm not going to put a box. Maybe to make it stand out, I will put a dotted line. Yay! And that'll be my indication. No, don't memorize that. That just know that if I get something where I need to eliminate initial velocity, I will. I'll solve that for initial velocity. I'll actually do this in 2 steps because, like I said, we could keep going on with this. And at some point, it just is best just to say, let's go back and look at these. Now, I'm going to wrap up this video now and say that here is my recommendation. That when you look at these 4 equations, if you bother to memorize all 4 of them, okay, which, like I said, is the advantage of you don't have to do 2 steps if you memorize equation 3 and equation 4. Unless you memorize equation 5, you are going to have to do 2 steps if you're trying to eliminate initial velocity. But I like to say what's neat about these 4 equations is to focus on what is missing. See, if you think about these 4 or 5 variables, what were they again? They were acceleration, velocity, distance traveled, time, and initial velocity. Now, looking at these 5 and these 5 equations, one variable is missing from each of these 5 equations. See, what is missing from equation number 1? It looks like distance traveled. What is missing from equation 2? Final velocity. What is missing from equation 3? Now this one should be obvious because we solved for time and substituted in. So time is clearly missing. What is missing from equation number 4? Well, hopefully, again, it's obvious because we solved it for equation 1 for acceleration and substituted in. So acceleration is missing. And what is missing from equation 5? Clearly, initial velocity. That's, again, we solved initial velocity in number 1 and substituted into here. Now, why am I focusing on what is missing? Well, believe it or not, my advice to you, if you've followed this long into the video, is to, as you do your one-dimensional motion, and if you see a problem with constant acceleration, you know you're going to be using one of these 4 or 5 equations. And if you focus on what is missing, because usually the question does this. The question will give you 3 variables and ask you to find for the 4th. And something will be missing from the problem. And that missing one you don't need. And so the equation you need is the one that has that one missing. I'll say it again. Typically problems like this that have constant acceleration, where these equations are valid. And let me emphasize, these equations are only valid with constant acceleration. So please don't use them in a problem that doesn't have constant acceleration. Okay, but in problems like this that have constant acceleration, you will usually be given 3 factors. You'll be asked to find the 4th, and 1 will be missing. So of these 5 right here, 3 will be given. You'll be asked for the 4th, and 1 missing. So if you can focus your attention on which one is missing, you can then focus your attention on which equation to use. That's the key I wanted to get at. And so I know this video went a little long. Hopefully it'll be helpful, but I'm going to say it one more time because this is the grand finale. Noting that these are the 5 variables, you will be given 3. Ask for a 4, 1 will be missing. Focus your attention on which one is missing in the description of the problem. Then use the equation that has that one missing, because then you can answer the question. All right? And actually, I should have, I keep saying 3 would be given, but maybe not, because you may not need 3. Like this one here is missing this one, but it only had 1, 2, 3, 4. Oh, no, it has the other 4. Never mind. Bad example. But anyways, focus on the one that's missing. That's really what I want to say. Focus on the one that's missing in the description, which will also focus you on which equation to use, and you'll nail these ones. All right, take care.